Okay, welcome. And now we're going to start analyzing arguments. Okay, so this is section 1D. Okay, so there are two types of arguments. One is going to be an inductive argument. An inductive argument starts with specific premises and then generalizes to a conclusion. Okay, so to a general conclusion. Okay, so you start with specifics and you go to general. So for example, here's a premise that we could have. We could have blue birds fly. That's specific, right? So blue birds fly. So that's premise. And then the second premise here, they said, well, hummingbirds fly. Okay. And then, a third premise is that cardinals fly. So we've got three premises, right? See, these are assertions, right? Statements that are either true or false. Bluebirds fly, hummingbirds fly, cardinal fly. So what's the conclusion? All birds fly. So that is an example of an inductive argument. Now, is it true that all birds fly? No. Ostriches come to mind. Emu comes to mind. Okay? Dodo bird? I think they're extinct, but I don't think they flew either. But anyway, you get the point. But this is an example of an inductive argument nonetheless. The second type of argument is called deductive argument. So that goes the opposite. It starts with general premises and ends with a specific conclusion. Okay? So these are general things that we look at, right? And then we conclude that it's going to be true for a specific example. So here's an example here. So we make a general premise that all doctors are intelligent, right? So that's general. It applies to all doctors, right? Second premise, Dr. Jones is a doctor. So now this is a premise that's specific, right? About a specific person, namely Dr. Jones, okay? And he is a doctor, right? So then what is the conclusion going to be? The conclusion is that Dr. Jones is intelligent. So we end up with a specific conclusion about Dr. Jones. Okay, so this is an example of a deductive argument. Okay, now, how do we evaluate inductive arguments? Inductive arguments are evaluated by their strength. Okay, how do we know how strong it is? It's how well cogent the argument is, meaning do the premises support the conclusion? Okay, are they well supported by reason? Okay, so this is where the fallacies come in. Okay, so an argument is strong if a compelling case can be made for its conclusion, which again is kind of vague, but what it means is that the reasoning behind it is strong. The reasoning behind it connects in a nice, cogent manner. And so we would say that, hey, if the argument is cogent, meaning that the reasons behind it are connected and are logical and follow, then we would say it's a strong inductive argument. Okay, and a weak argument would say, well, it's not well supported by the premises, right? Maybe it suffers from one of the fallacies that we've studied before. So let's look at this example here. So it says a movie director tells her producer, who pays for the movie, not to worry. Her film will be a hit. As evidence, she cites the following facts. She hired big stars for the lead roles. She has a great advertising campaign planned, and it's a sequel to her last hit movie. Explain why this argument is inductive and evaluate the strength. Okay, so let's go with inductive. Okay, so now listen. So it starts with specific evidence, right? Specific pieces of evidence, reasons why she believes the movie is going to be a big hit. And the director uses these facts to support her conclusion that the movie will be a hit. Okay, now because the conclusion is more general than the premises, the argument is inductive. However, the argument is relatively weak because even best planned movies can flop, and we can all know sequels that flop. We all know movies that have big name actors that flop, and we all know movies that have great marketing campaigns that still flop. Okay, now evaluating deductive arguments, that's a little different. Okay, so we're going to apply two criteria to evaluate deductive arguments. Okay, we're going to talk about validity. An argument is valid if the conclusions follow necessarily from the premises. Now, we don't care at this point whether the premises are indeed true or not. Okay? All we care about when it comes to validity is whether the premises, if they were true, automatically follows or has to follow that the conclusion must be true. Okay? That's how we decide validity. We always say, okay, if the premises are true, does the conclusion necessarily follow? Okay, if so, it's valid. If it's not necessarily true, then we would say it's invalid. And we've seen some of these before, and we'll talk more about that momentarily. Now, an argument is sound if the premises are indeed true and it is a valid argument. Okay, so again, valid, so sound goes one step further than valid. Valid means if the premises are true, then the conclusion must be true. A sound argument is an argument that is valid and the premises are in fact true. So sound is a much better argument. It's the best argument because it's non-refutable. Okay? A valid argument can be valid but unsound. Or how much is that right? Hold on, let me. A valid argument. So let me say it this way. A sound argument must be valid. A valid argument doesn't need to be sound. Okay, so here's the gist of both inductive and deductive arguments. So I would study this. You can print this off, keep it in your folder, study it. These are the takeaways for what we just went over. Now, we can use Venn diagrams to test the validity of argument, and I think it's a great tool to use to help visualize when an argument is valid or invalid. And this is for deductive arguments. When it comes to inductive arguments, that's where our fallacies come in that we studied at the beginning, okay? Now, when it comes to deductive arguments, we're all about validity, okay? So now let's use a Venn diagram here. So one, draw a Venn diagram that represents all of the information contained in the premises. Step two, check to see whether the Venn diagram confirms the conclusion. If it does, then the argument's valid. Otherwise, it's invalid. So let's look at this example here. So we know this from before, right? So here we have our concentric circles. And so our argument is that one, what? All fish live in water. So that's one premise. Whales are not fish. That's premise number two. And then the conclusion is whales do not live in water. Okay, now, obviously this is not true. So this is invalid. Okay, now, how do we show that it's invalid? Well, one way is to ask ourselves, okay, does the conclusion necessarily follow if the premises are true? So in this case, the two premises are in fact true, but we all know whales do live in water. So the conclusion does not follow from the premises. So it's invalid. So we know it's invalid. Okay, but how do we show that with a Venn diagram? So when we say all fish live in the water, we're saying all animals that are fish, right, live in the water. Okay, so they're going to be part of everything that lives in the water. So all things that live in the water is going to be one circle. Fish is going to be another circle, and fish are going to be inside the bigger circle, which represents all things that live in the water, right? So now once we have that set up, and of course we have our rectangle, which represents all living creatures or all animals or whatever you want to name it. Okay. Now, it says whales are not fish. So whales has to be outside the pink circle. But where outside the pink circle? Does the conclusion necessarily follow from the two premises? Well, it doesn't, because there's nothing in the argument that tells me whether the X has to go in the blue or whether the X has to go in the green region. So since it's not clear where I should put the X, we put it right on the border of the two, which indicates where we're not sure. And of course, if we're not sure, it's an invalid argument. Now, another way to show or see that an argument, a deductive argument is valid or invalid is by the structure. So validity really comes down to the structure of the argument. We don't care what's being said, it's the structure. Okay? Whether the premises are true or not is irrelevant. We just look at the structure. So here are the 4 common structures that we're going to study. Okay, well, there are other structures that we'll mention, but these are the 4 common ones. Okay, so the first structure is affirming the hypothesis or the antecedent, right? So modus ponens is the Latin. So affirming the antecedent. So this is always valid. So anything that has this form is valid. So if you have a conditional as one premise, followed by the affirmation of the antecedent, right? P is the antecedent in this case. So you're saying P is true, so that's affirming the antecedent. So if you have a conditional followed by an affirmation of the antecedent, and then of course the conclusion is the fact that Q is true, right? So this is basically just stating what we know about implications, right? We know that if P is true, then Q must follow, right? That's how we have a true conditional, right? Remember back when we were studying truth tables and conditional statements, we know that the only time that a conditional is true is the only time it's false is if the P is true and the Q is false. So if the P is true, right? And the way an implication works, that if the P is true, right, then the Q must be true. Okay, that's how conditionals work. If my son gets an A on his spelling test, and I say if he does, he's going to get ice cream, and he gets 100% on his spelling test, then if I don't take him out for ice cream, then he's going to call me a liar. So the conclusion must follow from the fact that he got 100% on his test. You know, I'm going to take him out for ice cream. So in this case here, I say, okay, son, if you get 100% on your spelling test, I will take you out for ice cream. He comes home. He gets 100% on his spelling test. That's like the first 2 premises, right? So premise 1 and premise 2. And so what's the conclusion? Well, I'm going to take him out for ice cream. That would be a valid argument. Anything else would be invalid. Okay? So if I have these 2 premises, any other conclusion would be invalid. Okay, so that's affirming the antecedent. Now, what about the second one? The second one is affirming the conclusion. So this is like having an implication and then looking at the converse, right? So remember, just because an implication goes one direction doesn't mean that it's necessarily true going the other direction, right? So think about it this way. If I say, if my son gets 100% on a spelling test, I will take him out for ice cream. Okay? That does not necessarily mean that if I take him out for ice cream, that he necessarily got 100% on his spelling test, because remember, he could get a 95 and I could still choose to take him out for ice cream or not, right? So it's not necessarily true going the other way. So the other fallacy, this is actually the fallacy of the converse, right? So we're assuming this is true, right? And then basically the second premise and the conclusion is the converse of the first premise. And so remember, just because you have a conditional, the converse is not necessarily true all of the time. So this would be an invalid structure, invalid form. Okay, now let's look at denying the antecedent. So this is where you start with the conditional, if P then Q, and then you say, okay, well, we're going to say not P, which we're going to say not P is not true. And then the conclusion is say, well, then in that case, Q can't be true. Well, is that necessarily true? No. Think about again about my example. I say, okay, son, if you get 100% on your spelling test, I'm going to take you out for ice cream. He comes home and he doesn't get 100% on his ice cream, or he doesn't get 100% on his spelling test. Does that necessarily mean that I am not going to take him out for ice cream? No, that's not necessarily true. I could have still taken him out for ice cream. Okay, this is also called the fallacy of the inverse. Okay, so this is an invalid form. Okay, now what about denying the conclusion or denying the consequent? This is the same as the contrapositive, because again, if you look at the first premise, that's the conditional, but if you take the second premise along with the conclusion, this is the contrapositive. Okay, so the contrapositive is always equivalent to the conditional. So if I say if P then Q, that's the same as not Q implies not P. So if I know that this is true, the first premise, and I give you not Q, that I know for a fact that not P has to follow. Okay, so this is true. This is valid by contrapositivity. Okay, so this is valid because it's just taking the nature of a conditional that we've studied, right? It's just using the fact of how a conditional works. This one is valid because it's just using contrapositivity. We know that if the conditional is true, then the contrapositive must also be true, which is the second premise along with the conclusion. So the second premise along with the first premise has to lead to the conclusion in this case as well. And then of course, the other two are invalid because the conclusion does not necessarily follow from the two premises. Okay, and if you remember, this is the fallacy of the fallacy of the converse, and this is the fallacy of the inverse. And remember, if you remember back to when we were studying truth tables and equivalence, we know that inverse and converse were equivalent statements, and also the conditional and the contrapositive were also. So there's a relationship there. So there's a link. So that might help you remember. Okay. Always use examples too. I love using examples to help remember these things. Okay, so here's an example. Affirming the hypothesis, we know this is a valid structure, but let's take a look at this. So the premise, it says, if a person lives in Chicago, then the person lives, if a person lives in Chicago, then the person likes windy cities. Okay, so that's premise number one. Premise number two is Carlos, a specific person, lives in Chicago. So the conclusion says Carlos likes windy cities. Now this is valid, and it makes sense because if premise number 1 is true, if that's true, and it's true that premise number 2 is true, then it necessarily follows that if the two premises are true, then it has to follow that the conclusion has to be true. Okay, and it does form the this does have the form of the affirm the antecedent. So let's look at this. Okay, let's use a Venn diagram. So here we go. All people who live in Chicago like windy cities. So we're going to have one circle that represents everyone who likes windy cities, and the pink circle are all the people who live in Chicago. So notice how the pink circle is inside the blue circle. Okay, so that represents all people in Chicago like windy cities. Okay, now Carlos is a particular person that lives in Chicago. So where does the X go? Well, it has to go inside the pink circle. But here's the thing. If you put the X inside the pink circle, then guess what? You have to also be inside the blue circle, which means that he has to like windy cities. So the natural conclusion must follow, which is valid. All right. Okay, so let's look at this one. Premise. If an employee is regularly late, then the employee will be fired. Premise 1. Premise 2. Sharon was fired. Conclusion. Sharon was regularly late. Nope. Is that necessarily true? Does the conclusion necessarily follow from those two premises? No, of course not. There could have been other reasons she was fired. She could have been fired because she told the boss off. She could have been fired because she broke safety protocol. She could have been fired for all kinds of numerous reasons, right? So just because she was fired doesn't automatically mean that she must have been regularly late. Okay, she could have been fired for being regularly late, but it could have been something else. So right away we can see that this is not a valid argument. But let's do the Venn diagram. Okay, so again, let's represent our circles, right? Our subject set and our predicate set, right? So we're saying here's a great one. If an employee is regularly late, right, then the employee will be fired. Guess what? Remember the all statements? Conditional statements are equivalent to all statements because if you say if an employee is regularly late, then the employee will be fired, then it means that all employees that are regularly late are also employees that will be fired. So there's concentric circles there. So conditionals are always translated into all statements, or they can be, right? So there's an equivalency there. Okay, so we have got concentric circles, and then Sharon was fired, so we'll have to figure out where the X goes, right? So here's our Venn diagram. So we've got the circle of regularly late people, that's the pink circle, inside the circle, the bigger circle of people who get fired or who will be fired. Okay, so now it says Sharon was fired. Well, all that means is that Sharon is inside the blue circle. But again, it's ambiguous as to where in the blue circle the X's should be put. Should the X be out here? Or is the X in here? It's not obvious. It's ambiguous, right? So since it's vague, ambiguous, then guess what? We put this X right on the border, and that shows us that this is an invalid argument. Okay? All right. Let's look at affirming the conclusion. Okay, now, hold on, let's go back. Okay, we already did this. Okay, here's the next one. Okay, it says, if you liked the book, then you'll love the movie. That's premise 1. Premise 2, you did not like the book. So the conclusion is you will not like the movie. Now, again, ask yourself, does the conclusion necessarily follow from the premises? So is it automatic if you like the book, then you'll love the movie? So let's say that's a fair statement. That's a true statement. If you like the book, then you'll love the movie. And then the premise is you did not like the book. Well, if you did not like the book, does that necessarily mean that you will not love the movie? No. No, even if the premise, let's assume premise 1 is true. Okay? Premise 2 has nothing to do with liking the book, right? So in this case here, all bets are off, right? So even if you did not like the book, you might still love the movie. It's not necessarily true that you will not love the movie, right? But let's look at a Venn diagram. So again, label your sets. So again, premise 1 is if you like the book, then you'll love the movie. That means if we look at this as an all statement, excuse me, we're saying all people who like the book love the movie. So that means the circle that represents all people who liked the book is going to be inside the circle of all people that love the movie. So it's a subset, right? So all conditionals are subsets, as we've seen before. Okay. Premise 2 is you did not like the book. Okay, so let's write that conclusion. Or excuse me, let's write that Venn diagram. Okay, so here's the diagram, right? Just like I said. And then, of course, the conclusion is you did not like the book, right? So now, again, if you did not like the book, all that means is that the X is outside the pink circle again. So that means you could be here, but the X could also be out here. Either way, you'd still be outside the pink circle. So again, it's ambiguous where to put the X. And so the X goes on the border and it's invalid. All right, now last one. Premise 1, a narcotic is habit forming. Premise 2, aspirin is not habit forming. Conclusion, aspirin is not a narcotic. Okay, so again, let's analyze this using a Venn diagram. Okay, but let's paraphrase some of this because it's a little hard to see what's going on here. Okay, so let's represent P as a substance that is a narcotic, and Q is a substance that is habit forming. So premise 1 would say, hey, if a substance, how can we do this? So we're going to say P is a substance that is a narcotic, and Q is a substance that is habit forming. So we can say if a substance is a narcotic, then it is habit forming. Premise 2 is aspirin is not habit forming, therefore aspirin is not a narcotic. Okay, so once we rephrase it, it's easier to see how we're going to do this. Okay, so again, we've got a circle that represents all of the narcotics, right? And then we've got that is a subset of all of the substances that are habit forming. Okay, there are obviously things out there that are substances that are habit forming that are not narcotics. Caffeine, nicotine, right? Now, the premise number 2 is saying that what? Aspirin is not habit forming. So where do we put the X? The X has to go outside the blue circle. Well, look what happens. Since it's outside the blue circle, it is also necessarily outside the pink circle, which means it's not a narcotic. So therefore, this is valid because there's no ambiguity, no confusion, no vagueness about where to put the X. So this is a valid argument. Now, let's do another type of argument that is deductive called the chain of conditionals, or in other words, it's called the transitivity, using transitivity. And this is also a valid argument. It's a valid argument because it's valid by what we call transitivity, right? So we've got a chain of conditionals. So think about math. If A is equal to B and B is equal to C, then it must be true that A equals C. That's true by transitivity. Okay, same thing similarly happens. A similar thing happens with conditionals, a chain of conditionals, right? So if we have if P then Q, right? So if this is true, right? And then we have if Q then R, and that premise is true, then the conclusion is if P then R. Well, think about it. If premise 1 is true, that if P is true, then it must lead to Q. And then premise 2 says if Q is true, it must lead to R. Well, then the conclusion says if P is true, then it must lead to R, which is true because guess what? It's like a chain. If P leads to Q and Q leads to P, then if P is true, then it must automatically lead all the way to R. And that's what the conclusion says. Okay. Now, incidentally, the transitivity property does not go the other direction. So think about the converse and the inverse of the chain. It works the same way. So those would be invalid. And I'll let you think about it. So that uses, again, some of the same things that we talked about before. We don't talk about it here, but again, just stuff to think about. Okay, so here. Here's an example. It says, if elected to the school board, Maria Lopez will force the school district to raise academic standards, which will benefit my children's education. Therefore, my children will benefit if Maria Lopez is elected. So let's figure this one out. Okay, so now premise 1, what are they saying here? It says if elected to the school board, Maria Lopez will force the school district to raise academic standards, which will benefit my children's education. So there's the two premises that are kind of connected in there. The therefore, that signals the conclusion. Okay, now one of the premises is if Maria Lopez is elected to the school board, then the school district will raise academic standards, right? That's right here. Okay. Then the which part, signals another premise, right? Which starts with the raising of academic standards. Right? So the which, think about it, the which, again, this is where grammar comes in and this is where you have to be careful. The which is connected to raising academic standards. So that will be the second premise. So the first premise is if Maria Lopez is elected to the school board, then the school district will raise academic standards. Then the second premise is going to be if academic standards are raised, then what will happen? It'll benefit my children's education. And so sure enough, there it is. And so what's the conclusion? Well, it's a chain of conditionals. So if Maria Lopez is elected to the school board, then guess what? My children's education will benefit. And so this is a valid argument. And so let's look at the Venn diagram, because now you've got three things going on. You've got P represents Maria Lopez is elected, right? Q is the district will raise academic standards. R is my children will benefit, right? And then you can create a Venn diagram from that. Okay, now we're not going to do that, but again, practice that. See what you can come up with. Okay, and then again, use the conditionals, right? Remember, the conditionals are all related to all statements, right? So use that to help you decide how the circles are going to be connected. Okay, now here's the other thing that we want to look at when it comes to induction and deduction. So more than any other subject, mathematics relies on the idea of a proof. Okay, a mathematical proof is a deductive argument that demonstrates the truth of a certain claim or theorem. A theorem is considered proven if it is supported by a valid and sound proof. Although mathematical proofs use deduction, there are theorems that are often discovered by induction. So we call those, in mathematics, we can prove things by inductive arguments. By the way, incidentally, there's also the proof by contradiction as well, which is a great argument and a powerful argument in some situations. Okay, so now here's an example of an inductive argument that tests this rule. So test the following rule. This is the commutative law, right? The commutative property for real numbers. Okay, so it says A times B equals B times A. Okay, so what do? How do we prove this inductively? Well, we start with specifics and we want to go to a general conclusion. Okay, so we start with an example. Okay, 7 times 6 equals 6 times 7. Correct, works. And we keep doing this over and over again a few times, right? Okay, and we show that it works every time. Now, the 3 test cases are each somewhat different. So some of them had mixing fractions, decimals, and negative numbers. Yet the rule worked in all 3 cases. This outcome offers a strong inductive argument in favor of the rule. Now, although we haven't proved the property, but we have good reason to believe that it's true. Now, the only way to do this is to use a mathematical inductive argument. And by the way, I'm not testing you on this, but what we do is we assume that it to be true for all values up to some k value, and then prove that it also works for the k plus 1 value. But anyway, you don't have to know that. All right, and that wraps it up for this section. Take care, and I'll talk to you later. Bye now.